In this lecture, we are going to prove Cauchy-Goursat theorem. Cauchy-Goursat theorem is nothing but the mathematician Goursat has proved the Cauchy theorem without assuming f that is continuous. If you recall the statement of the Cauchy theorem, if you recall the statement of Cauchy theorem, if these are simply connected region, simply connected region, region fz is continuously differentiable, that is continuously differentiable in the that is fz axis and continuous in the then integral c fz dz is equal to 0, where c is my closed contour contained in D, where C is closed contour contained in D. Goursat has proved this Cauchy theorem without assuming that fz is continuous. That is the statement of the Goursat theorem, Cauchy-Goursat theorem. Let fz be analytic. In a simply connected domain. Domain D, and C is closed continuous rectifiable curve, rectifiable curve in D, then integral C fz dz is 0. There are three alternative proof of Cauchy-Goursat theorem. Here I will give only one method of proving Cauchy-Goursat theorem. You should, other two is your home assignment. You should try your own. In case of any problem, you can ask me. Now, proof of the Cauchy-Goursat theorem. First, to prove this theorem, we have to prove a lemma known as Goursat lemma. So, right, first to prove this theorem, we will prove the following lemma. Prove the following lemma. Following lemma. Following lemma known as Goursat lemma. Goursat lemma. This lemma, statement of this lemma, let fz be analytic within and on closed contour C, within and on closed contour C, then for epsilon greater than 0, it is always possible to to divide to divide to divide the region within C into finite number of squares squares and partial squares squares of boundary SI ranges from 1 to up to n. Then there exists a point Zi within each SI such that this inequality whole f of z minus f of zi minus z minus zi minus f dex zi less than epsilon for all z not equal to zi within or on SI. That is, if fz is analytic within and on a closed contour C, then for epsilon greater than 0, it is possible to divide the region within C into a finite number of square and partial square of boundary SI. And within each SI, I will always find a point Zi for which this inequality 1 whole, where Z is not equal to Zi. Okay. Now proof of the lemma. Proof of the lemma. We shall prove this. We shall prove this lemma by contradiction method. Okay, that is, for epsilon greater than 0, however small, there exists at least one mesh square or partial square or partial square for epsilon greater than 0, there exists at least one mesh for if we divide the region within C, the inequality 1 does not hold. The inequality 1 does not hold. That is, if you draw the figure, suppose this is our closed contour C, then with the help of line parallel to the coordinate of axis, we will divide this region into finite number of square and partial square. I will tell you what is square and what do you mean by partial square. Here, the side of the square which lies along the contour is known as, this square is known as partial square because one side lies along the contour, or the curve is so large that this side will be a straight line, and these are squares. So here we have considered for epsilon greater than 0 there exists at least one mesh for which if we divide the region the inequality 1 does not. Next, let let R denote the region within region within C. Okay, we divide R into finite number of finite numbers of square and partial square by means of the line drawn parallel to the co- coordinate axis. As per our assumption, as per our assumption, as per our assumption, there exists at least one mesh, one mesh. It may be square or partial square, partial square, partial square, partial square, for which inequality 1 does not hold. Let this square or this mesh, be sigma naught. It may be square or partial square. It may be square or partial square. We divide sigma naught into 4 equal squares. Then there exists at least one subsquare of sigma naught, for which 1 does not hold. Let this be sigma 1. Then again divide this sigma 1 divide this sigma 1 into 4 equal square into 4 equal e- equal into 4 equal square. If this process terminate after finite number of steps, then we get a contradiction. We get a contradiction, and hence lemma hence the lemma is true. The meaning is, suppose one of this square be sigma naught. This is sigma naught. Suppose this square is sigma naught. This is the orientation of the contour. So if we divide this into 4 equal part, if I magnify this square, if I divide it into 4, this is my sigma naught. This is square sigma naught is this one. If I magnify this one, if I divide it into 4 equal parts, then there exists at least one square which contains this point, for which the inequality 1 does not hold. Again, if we divide this square that contains that point into 4 equal square, again from this 4 part I will get one square where this inequality does not hold. Again, if I divide this, again I will contain this. If the process terminates, then it is a contradiction to our hypothesis. But if it does not terminate, we will get a sequence of squares. So if the process terminates after finite number of terms, then we get the contradiction. And hence the lemma is true. But if the process if the process continue indefinitely continue indefinitely indefinitely indefinitely, then we will get a sequence of squares, sigma naught, sigma 1, dot dot dot, sigma n, dot dot dot, is contained in the previous one. Is contained in the previous previous one previous one for which inequality 1 does not hold. Inequality 1 does not hold. Does not hold. Consequently, there exists a point. There exists a point z naught, which is the limit point, which is common to all this square, which is common to all these. I have shown you this one, which is common to all these squares, and this Z naught act as the limit point of this set. All this square and and this point Z naught act as act as limit point of the set of points in R. Also Z naught belongs to the region R, as R is closed. In the statement of the theorem, it is given f z is analytic within and on the closed contour C. Therefore, f is differentiable within and on C. So, right, since f z is analytic, since f z is analytic, f z is analytic, f z is analytic within and within and within and on closed contour within and on closed contour within and on closed contour C. Therefore, fz is differentiable. Therefore, since z naught belongs to R is the region inside C. Therefore, fz is differentiable. Is differentiable at z naught. Is it z naught? That is in the modulus fz minus fz naught by z minus z naught minus fx z naught modulus less than epsilon. Put this equation 2. This happens for all z, for all z minus z naught less than delta. Next, we choose a positive number. We choose positive number and solars that the diagonal of the sigma n square solars that diagonal of the diagonal of sigma n square of square sigma n is less than delta. Okay, thus all the sigma capital M for all n greater than equal to n are contained in the neighborhood are contained in the neighborhood z minus z naught less than delta. Okay, of z naught. Okay, that means this is our square neighbor. This is our sigma n for large n. This is sigma n. Z naught is contained in here. This is the neighborhood. This is circular neighborhood. You should draw properly circular neighborhood such that all this sigma n is contained in this neighborhood. Also, Z naught belongs to sigma m. Okay. Thus there exists a point Zi. Here in our case, it is Z naught. Here it is Z naught. Within each Si for which inequality 1 holds, which contradict our hypothesis, contradicts our hypothesis, which is contradiction to our hypothesis. Hence the lemma is true. Next, we are going to prove the theorem. Proof of the theorem. Proof of the theorem. Proof of the theorem. Proof of the theorem. Next, we will write inequality 1 in this form. This inequality can be written in the form this. We have this f of z minus f of zi, z minus zi minus f times zi less than epsilon. So this can be written as f of z minus f of zi. If I take this to right hand side, it will be this one. Then this is z minus zi. If I take this to right hand side, it will be plus fx z. Now in place of epsilon, since epsilon is arbitrary positive number, so we will going to put some function eta z here, where eta z will be, value of eta z will be, magnitude of eta z is less than epsilon. We have to choose eta z in such a way that if we put this in this inequality, the inequality sign holds. Okay, it does not create any change to the inequality sign. That is, we will get this one. So right, inequality 1 can be written as this. Put this equation 3. Since 3 gives the value of z, the value of fz at any point, at any point on the boundary of Si, therefore integrating 3 around, integrating 3 along Si, we get, take the integral along the Si, so we will get this one. integral along SI fz dz is equal to, this is, if I take this, this is f of zi, okay, no f of z. So this will be my f zi minus, here our variable of integration is dz, so take the constant, that is I'm writing this with this one, this with this one, I will take this differently. So rearranging and writing, we will get this one, integral si z minus zi or fz, fzi, 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 fzi minus z fz zi. This is z or zi, zi, zi d of z. Okay, then write the next one, that is plus integral around si, then z fx zi will be taken outside, fx zi will be taken outside, this is z dz, then plus is integral around si, then we have eta z, there will be one z minus zi with eta, because when we put the epsilon equal to eta z, then it will, if we multiply this with this one, then after that we will multiply this z minus zi to epsilon. So here we will get z minus zi. Okay, so you should, before writing eta z, you should write this, before writing eta z, you should write this z minus zi, z minus zi, eta zi. Okay, so here we will get z minus zi, z minus zi, eta zi, eta z, eta iz, d of z. Eta I, this will be the, this is not z, eta I z. Put this equation 4, put this equation 4, and this will be here, the value of this integral is 0. If this is here, our differentiation is with respect to dz, so this can be taken outside the integral sign. In the next step, do not put equation 4 here. After simplification, we will going to put this equation 4. That is, we can take this outside, we can take this outside, fzi minus zi fx zi can be taken outside, as our differentiation is with respect to dz. Again, this is f(x) z I integral si z dz. Okay, plus integral si z minus zi I z dz. Okay, the integral as dz is 0, as here integrand is 1, and again this is a polynomial function, so it is differentiable. That means it is our integrand is analytic, and si's are the closed curve, so integral along the closed curve is always 0 by Cauchy theorem. So these two values are 0, this values is 0, we will left with this one. So write this. Now put the equation O. Si z minus zi, then ida I z dz. Right? Since integral along si dz is 0 and the integral along si z dz is 0. Now you can check out in the diagram. Yeah, the integral along this curve C is equal to sum of the integral along this square, because the this square and this side, the adjacent side will cancel each other. The side common boundary of every adjacent mesh will cancel each other. The common boundary of every adjacent square or partial square will cancel each other, so, and we will left with this integral along C is equal to integral, that is integral along C is equal to sum of integral along is square and partial square, because the adjacent side will cancel each other. Okay, common side of the square and partial square will cancel each other. So this write this this is our integral along si fz dz, and put this equation 4 and equation 4. Now put this equation 4 and write the integral around the closed curve or closed contour C is equal to the sum of the integral around si, because because the integral along the common boundary along the common boundary of every pair of adjacent mesh will cancel each other. Will cancel each other. Cancel each other. Therefore, integral along C fz dz equal to sum of integral over si fz dz I ranges from 1 to n Now from equation 4, we have seen that integral f z dz si is equal to integral over si z minus zi eta I z dz. So put this value, you will get this one, summation I ranges from 1 to n integral si, put the value, this is my z minus zi eta I z dz. Okay, now so put this equation 5. Now take modulus on both sides, fz dz is equal to sum over I ranges from 1 to n integral si z minus zi f of not f eta I. Here it is eta I z dz. If you expand this by using the properties of modulus and rewrite this equation, that is integral s1 like this, integral s1 z minus z1 eta 1 z dz plus modulus this plus modulus integral s2 z minus z2 eta 2 z dz plus dot plus integral Sn z minus zn eta n z dz. So in summation notation I can write this I ranges from I ranges from 1 to n summation I ranges from 1 to n modulus of si z minus zi eta I z dz, that is less than equal. Here it will be less than equal. Okay, less than equal because I am using the property of magnitude. So this is equal, this is not less than equal, it is less than equal, other is equal, less than equal, and this is equal because I am adding these things. Now by the property of definite integral, that is this integral fz dz over c is less than equal to integral over c fz dz and this. Using this property I am rewriting this, I will bring this modulus inside and rearranging this will be less than equal to sign here from here. So wrap this one. Using this property I will rewrite this one, that is integral fz dz is less than equal to integral, this is less than equal to sum over I ranges from 1 to n integral si modulus of z minus zi modulus of eta I z eta I z eta I z modulus of dz. Okay, and this is equal to this eta I z is less than epsilon. Here we have considered it in the beginning when we write the inequality in the inequality 1 in the equation form. This one is the eta z is less than epsilon, So I'm using this value of eta z here. So this will be again less than sign. This will be again less than sign. Less than epsilon, then sum over I ranges from 1 to n, sum over si z minus zi dz. Okay, put this equation. What is the last equation we have given? 5. So this is equation 6. This is little bit lengthy theorem. So write this. Next, let ai be the length of the side of the square the point z lies on si and zi lies inside si. Okay, inside si. Our point z lies on si, that is on the boundary of si. This is the square. So in the boundary, the point z lies. The point z lies in the boundary, and zi lies inside the boundary. So that this distance between z and zi is always less than the diagonal of this square. Right? That this distance z is also always less than the diagonal of the square. We know that the side of this square is a, so this our diagonal will be a square plus a square. That is using the Pythagoras. We will get diagonal is equal to this is equal to diagonal will be root over of this, so this is equal to root over 2a square, that is equal to root 2a. So this z minus zi is always less than root 2a. Okay, so write this. I have written the point z lies on si and zi lies inside si, so that the distance between z and zi is always less than the diagonal of the square diagonal of the square. Here it is. Here we have considered area is the side of the square, so diagonal length of here length of diagonal is length of diagonal of si is a root over ai root over 2 for all high ranges from 1 to n. Okay, that is the distance between zi cannot exceed this range. This one is always less than diagonal of the square. Yes. That is z minus zi is less than equal to ai root 2. That is, therefore our integral si integral si integral si z minus zi dz is less than equal to, now we put the value of this one in place of this. I will put this value ai root 2 dz. In the next line, take the constant term outside, we will get this. This implies integral si dz minus zi. This is z minus zi dz is, it is less than equal to, less than equal to, it is less than equal to ai root 2, because our now differentiation is this and it is taken over as si. Put this equation 7 since 6, this is equation 7. We know that in the lecture of example of complex integral, we know that this is, what is this? This is the length of rectifiable curve si. Here it is our square, and length of square is the perimeter. Okay, here our length of square is the perimeter of this square. Length of rectifiable curve is the perimeter of this square. That is perimeter of this square. Perimeter, length of curve is the perimeter of this square. Length of si, which is equal to 4ai if si is the square. If si is square, okay, and si is equal to dz equal to 4 is less than 4 ai plus li. What is if s is partial square? Partial square, where li is the contour c, where li is the arc c, right? Arc, not contour. Arc c, arc c, arc of c that form the partial square. That form the partial square. Okay. Now substituting this value, we will get in 7. If we substitute this value in 7, we will get, therefore 7 becomes, therefore equation 7 becomes integral, what is 7? Integral si z minus zi mod of dz is equal to 4ai if si is square and it is less than equal to 4ai plus li if 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 si is partial square. in the diagram, in the diagram, if we enclose this contour by a square of enclose this contour with a square of side A, with a square of side A. Okay, this side is your A. So right, so right, we enclose the contour C with a square of side A, then obviously AI square, then AI square does not exceed A, does not exceed A, A square. Here, here we have considered the length of this square is AI. Okay, this length is AI. Then this square, this AI square will never exceed this A square. So write this. We enclose the contour with a square of a side with with length A. Then obviously AI square sum of, okay, not only one, sum of AI square, sum of user record, sum of sum sum yes sum of sum we enclose the contour C with a square of side length A, then sum of AI square does not exist does not exceed exceed A square. Okay, sum of is a small square area does not exceed the greater square that enclose the contour. Okay, next write if L denote the arc length of C, then we have integral C fz dz is less than epsilon. Then here, since we have already discussed that the integral around the contour is equal to sum of the integral along the squares, because the side common to both the adjacent mesh will cancel each other. So here we will consider the formula. That means formula for partial square. That is, here I am considering this integral is equal to sum of the integral of each square and partial square. But here all the adjacent mesh, the boundary common to the both the square and the square and the partial square will cancel each other. So we will left with this one. So in the formula we will consider the consider the integral along the partial square. Okay. So we what is the formula for partial square? That's 4ai alpha I 4ai. What will be the formula for this one? Finally, correct is there will be one ai square root 2. This will be there will be one a high square root 2 ai a y, that will be square, and there is 2 square root 2. The here before writing you should correct this one. That is nothing, but if we put this value here, it will be 4 root 2 ai. Okay, 4 root 2 4 root 2 ai. The ai is outside the root 2. Here also it will be 4. This is just writing mistake, nothing else. 4 root 2 ai. Okay, that is we have put the value of this one here. Again, value of this one here. When this will be, these are all less than equal to sign. This is less than equal to. This is less than equal to. Okay, less than equal to. Because here in 7 it is less than equal to sign. So, and the region why we consider this one is the, we have taken integral around the closed contour C is equal to sum of the integral around the partial square, and the adjacent boundary common to adjacent mesh will cancel each other. So we will consider this one, that is we will left with the only contour side partial squares. So we will consider this formula, that is 4 root 2 ai plus 4 root 2 ai square. This one is also ai square. ai square 4 root 2 ai square plus I ranges from 1 to n, and this is equal to less than equal to our, since this is containing, this is less than equal to a square, this is less than equal to this a square, and 4 root 2 a square plus summation of all this small length will be, these are li will be always less than equal to this length. This will be always less than equal to this arc length. Here it will be again, I have done one mistake, that is this ai root 2 will write in front of here. There is one mistake, you should correct this one. There is one mistake. Yeah, that was done here. Yeah, you should correct this mistake. That is, what is it? AI root 2. AI root 2. Then for AI, for AI, for AI. Uh, that is, this is, if I expand this one, then this is show for for ai square, and this is plus, this will be here, this will be your ai root 2. This is right properly ai l then root 2. Okay, this is root AI Li no? Li root 2. So now put this value, you will get this one. So correct this one, correct this one. We will ultimately get the answer 4 root 2 AI square, 4 root 2 AI square plus AI Li root 2. Okay, and this is equal to your, this is less than equal to, if I take summation simple, then within bracket it is 4 root 2 sum over AI square is always less than A, and here A L is it. This A is a constant, A is the side of the square, L is constant, it is the length of her. That means this is equal to epsilon into constant. Epsilon is a very small positive number. As epsilon is a small positive quantity, if I multiply this with some constant term, it will further smaller than the smaller, because consider epsilon equal to 0 1 and some 4, it will be zero point 0.4, it will be 4 or 4, it will be further smaller 4, if it is 4 like this, it will be further smaller, it is a smaller quantity. That means the value of inside the modulus is 0. That is modulus integral c f z dz is 0. This implies integral c of z dz is equal to 0. Hence the proof. With that, I would like to conclude. Remaining will be in the next lecture. Thank you.